Mount Edziza in northwestern Canada is a member of one of the most elite classes of mountain on the planet, called glacial volcanoes, volcanoes that erupt in contact with glaciers. Born from the union of incompatible parents, the conjugal mixing of flowing magma and rock-hard glaciers, the union of ice and fire. And yet the mountain in its evolution would change the course of early man and incubate from its devastation some of the Earth's most primitive life forms. This is the story of the consequences of joining fire and ice, and the life that sprang from their ashes. Edziza is a complex of 50 volcanoes, a symphony of epic proportions, written in a script of geology upon a parchment of time. From the escarpment-built layer upon lava flow layers, reaching back across vast basalt aprons, punctuated by volcanic cones, ascending finally to the crowning citadel of stone spires. It is an opus of tranquility and splendor, composed from violence and chaos. Using geological techniques such as carbon-14 dating of rocks, we can form an outline of the mountain's evolution. The Edziza volcanic complex is part of the Stikine seismic belt, running north-south along the interior west coast of British Columbia and into the Yukon. This volcanic belt was the result of the subduction of the Pacific plate sliding beneath the advancing North American continent. It is believed that the first volcanic activity in the Edziza region began 8 million years ago, midway along the complex, damming a river, creating a lake in its lee. Volcanic vents opened beneath the lake, creating subaquatic mounds of basalt pillows that grew until the lava rose above the lake's surface, eventually filling and draining it. Following a period of dormancy, a new series of steam vents, geysers, and mud pots began to appear on the flanks of the first eruption, heralding the second period of vulcanization. Magma soon flowed to the west and south, until even the earlier formations were buried. The most extensive volcanic events on Edziza, called the Nido period, were not localized to a single volcano, as magma flowed out of 6 major volcanic cones and dozens of lesser formations covering much of the complex. Fire fountains of gases and magma were common, and ash vents darkened the sky and masked the sun. After a long period of glaciation, another major vent opened, spilling sticky, viscous lava that adhered to the sides of the volcano, building a mountain that is today Mount Edziza. At the zenith of this volcano's growth, it formed a peak rising at least 600 meters. Then suddenly, the mountain blew its top, demolishing the upper regions of the cone, weakening the eastern flank of the crater. Lava lakes formed in what was left of the Mount Edziza cone. And again, pressure built up in the magma chamber below until it blew out the eastern wall, exposing the caldera to glacial erosion. There was a period of 500,000 years of semi-dormancy before a new series of volcanic activities began throughout the complex, sending vast blankets of fluid basalt and ash flowing across the apron. As the lava flows subsided, great cinder cones formed as the parent vent spewed mountains of ash and pumice around the flanks of the Edziza complex. Edziza is a mountain of mystery, both spiritually and scientifically. And though we have learned much about its origins, there are still intriguing questions about what happens when nature mixes fire and ice. Is it possible, for example, that some forms of life actually flourish because of this combination? Mount Edziza Obsidian is thought to be some of the best in the world. Is it possible to fingerprint it by using advanced technology to map native trade trails from their source to the far reaches of the artifact's journey? Also, although the surrounding mountains are granite, the Edziza complex is a mountain of glass, raising the question why. What is it about the consistency of its subterranean magma vaults that creates a landscape so unique? To address these questions, a diverse team of scientists made up of a volcanologist, archaeologist, and even a lichenologist converged upon this volcanic complex to look for answers. It is not the way that lava flows, but the way it cools that changes landscapes. By studying the way lava cools, we can understand the details of the mountain's evolution. Ben Edwards is a volcanologist who has studied around the world the bizarre consequences of mixing fire and ice.
One of the things we have to have happen before a volcano can erupt is we have to find a way to get the liquid rock, the magma, up to the surface to form a lava flow. And one of the most common ways that happens is that the earth actually cracks open, and then the magma or liquid rock can come up through the fracture. And here at Pillow Ridge, we have some really spectacular examples of that. So this wall of rock right next to me looks like it's a vertical face. But as you look in this direction and down in this direction, you can see it's continuous. And this is something that we call in geology a dike. It's a fracture that's opened up it's cut through the layering in the rocks, and it's vertically transporting liquid rock up to the surface to form pillow lavas or lava flows. A lot of times when a volcano erupts, we think about the volcano shaping the surface of the earth. And what you don't always think about is that actually sometimes the surface of the earth affects the volcano when it erupts. And so if you go to the ocean floor, or if you go to Hawaii where lava flows are coming into the water, we actually find a special kind of lava that is recording the fact that the lava is going into water. And that's called a pillow lava. So you might wonder why we're talking about pillow lavas up here at 7,000 plus feet above elevation on the north flank of Mount Edziza, because certainly we're a long ways from water, at least that's what you'd think. But this is actually a pillow lava. And this is a pillow lava just like the ones that are in the ocean floor or off the coast of Hawaii that formed into water. And how did a pillow lava get here? We're so far above the water, this is a mystery about the volcano. And there's really only one way that you can get water up this high, and that is to have ice around. Because when you have a glacier, even if you're up this high, if you melt the glacier, it can form a lake.
A new vent opened, and hot magma ate away at the glacier cap, producing a lake out of which an elongated ridge called a pillow ridge formed beneath the lake.
Now, pillow lavas, when they go into water, because the water makes the lava cool faster, the lava tends to take a shape that's more rounded. And a pillow lava is almost like a tube of lava that's going out into the water. And the very edge of the tube is covered by volcanic glass because it cools in such a way that crystals can't form before it solidifies. This is a typical cross-section through pillow lava, and it shows us lots of things about what was happening during the course of the eruption. Most lavas, to get to the surface of the Earth, they have to have some gas in them, and that's one of the ways that they can come up to the Earth's surface. And as they get closer to the Earth's surface, it's sort of like taking a bottle of soda and slowly unscrewing the lid. You can hear the hiss of the gas that's being released. Well, in lava, the same thing happens. When it's down deep in the Earth, we call it magma, and it's got gas in it, and as it comes closer and closer to the surface, it's sort of like you're slowly unscrewing the bottle on your soda, and gas starts to leak out. Now, some of that gas actually comes to the surface, and that's one of the ways you can monitor active volcanoes. You can actually detect the gas that's coming out even while the lava is down deep below. We can actually record some of the changes in pressure as this lava pillow came into water and then stopped and slowly cooled and crystallized, because you can see these rings of bubbles that formed at different times as the magma was slowly cooling from this outer edge, which actually has a thin rind of volcanic glass, up into the middle. Now this pillow is actually very, very interesting, because the pillow lavas actually act as tubes for more lava to flow through them, so it can go out further in the water. And you can see a couple of interesting things in this one. There's actually a hollow. I can stick my hand way back up in here. And what that means is this pillow tube acted like a conduit for lava to keep flowing through, and in the end, when this solidified, it wasn't filled with lava. So some of the lava had drained out and it left this lava tube inside.
Besides forming melt lakes that alter the way lava cools, glaciers also influence volcanic activity by their sheer weight.
When you load the crust of North America, the continental crust, with large amounts of ice, when we had the ice ages, you formed big ice sheets that covered Canada. And when you load the crust with all that ice, you actually press the crust down. It's remarkable that thickness of ice can depress the crust hundreds of meters. And that creates stresses in the crust, which will cause the rocks to fracture, actually. And you can imagine in a place where you're at the threshold of the release of lavas, magmas from shallow depths in the crust, if you create those external forces, the loading of the crust, that it will trigger volcanic activity. In the case of Mount Edziza, you get a lot of evidence that eruptions occurred when there glaciers in the landscape. And that's not coincidence. It's this kind of association between the loading and the unloading that is probably triggering a lot of this volcanic activity.
Ice can also serve as a record of volcanic events.
But Mount Edziza has a twofold history. Sometimes it erupts basalt lava flows, which are very fluid, can travel very far, but other times it erupts lava flows that tend to be explosive, like Mount St. Helens, like Mount Pinatubo. And those lavas that are explosive tend to have a different chemical composition. And that's one of the reasons why they're more explosive. And Mount Edziza has a history with at least 5 different episodes where you had basaltic eruptions forming large lava flows that filled valleys, followed by lava flows that were much thicker, didn't travel as far, and sometimes were explosive.
Another key to unlocking the mysteries of Mount Edziza's evolution is written on the glaciers themselves.
So ice can preserve records of volcanism. And one of the ways it can happen is that when a volcano erupts and produces an ash layer that covers the ice, more snow falls on top of the ash, and then the ash gets trapped inside the ice. And we see this in lots of places in the world. So that may well be what we're seeing in at least some of the layers in this stranded chunk of ice here in this moraine. Some of the layers may be layers of ash that are recording explosive eruptions that happened in the history of the volcano, the most recent history. So for example, when you look around this terrain, this is very classic for what we call ground moraine. It's material that would have melted out of a glacier as the glacier was slowly retreating back up to the mountain. But this ground moraine is special and kind of interesting because it actually still has some ice. So if we look across at the wall behind me, all of these lineations that you see in the ice are layers of dirt that formed on the surface of the ice and then were buried by more snow, which turned eventually to ice. One of the special things about this particular ground moraine is that it holds clues to a very important part of the volcanic history of Mount Edziza. Many of the eruptions at Mount Edziza produced lava flows and maybe small fire fountain eruptions like we see in Hawaii, where you may get ash and tephra thrown into the air for maybe a kilometer, maybe less. But we know from looking at the ground around us and the material in that ice that Mount Edziza sometimes doesn't erupt in a passive way like Hawaii. And sometimes it actually has explosive eruptions where rocks get shot up into the air for 5, 10, even 15 kilometers.
While the geological history of Edziza is mapped in millions of years, its natural history is both Spartan and recent. Wildlife on the complex is infrequent and often limited to a few nannies with kids finding sanctuary in the basalt cliffs, or a cow, caribou, and calf on the vast isolated pumice plains where predators can be seen kilometers away. Plants survive by sheer acts of their will and are often isolated to small oasis streams that vent out the sides of barren hills of ash and pumice. Human history on Mount Edziza has been confined to the last few thousand years, and it is believed that early migration routes of the hunter-gatherer passed along the west flank of Mount Edziza, leading to the first discovery of the mountain's obsidian sites. This material would prove invaluable for making tools, weapons, and would become the basis of a flourishing trade network. For suddenly, Paleolithic man had a substance so sharp that it could pierce even the toughest of animal hides. The first Europeans to venture into the Northwest came with the discovery of gold in the surrounding Cassiar Mountains in the mid-1800s. In 1866, the Collins Telegraph line to connect North America with Europe was strung through Edziza's Raspberry Pass. The line never reached Russia due to the successful completion of the transatlantic cable. In 1972, the Mount Edziza volcanic complex was made into a provincial wilderness park. There are no services available, requiring backpackers to be self-sufficient and carry both food and shelter for treks that range from 5 to 10 days. Access to the park is by float plane to one of the 3 trailheads. Buckley Lake at the north end of the complex, Modaddy Lake midway along the eastern side, and Little Ball Lake at the southern extremity. Starting at Buckley Lake, the first section of the trail serpentines through a vast labyrinth of lava beds less than 2,000 years old. Uneroded by glaciers, it is the landscape of cinder cones and gargoyle gardens. The trail through the midsection of the complex skirts the main peaks to the west, arching around tongues of glaciers before giving way to a great moonscape desert where plant life is the exception. Unlike other great deserts of sand, this section is covered with pumice dunes sandwiched between great ash and cinder cones. The southern terminus of the park is the Spectrum Range, named for its kaleidoscopic splendor, a geological palette of brilliant earth tones, rust-red irons, The iconic jewel in the cluster of volcanic brilliance is Kumagoo Mountain, towering above Little Ball Lake. The influence of mixing glaciers and vulcanization is not limited to creating or destroying mountains. Glaciers are depositories of the wind, not just ash and pumice, but also life forms such as seeds, spores, and pollen from around the world are deposited on glaciers. As glaciers recede, the potential life forms often settle into an alien and inhospitable environment and never take root. But what happens when they settle into a volcanic hot springs? Lichenologist Patrick Williston came to Mount Edziza to explore this question. Hot springs are often evident by the formation of outcrops of pure mineral salts. Meltwater from glaciers filters down through the porous, mineral-rich layers of lava, where it is heated by subsurface vents, causing the hot water to dissolve the minerals, such as magnesium. Once upon the surface, this salt-saturated soup flows out over the vegetation, slowly crystallizing and fossilizing the plants in its path.
So what's happening right around here is that the seepage is coming over and flowing over some of the plants like this grass, and in certain places it will precipitate around the grass and effectively petrify the vegetation. So you have this, in this case, a sedge. It looks like a sedge that's now turned to stone. So what we have here is some recent mineralization on the actual stems of the monkey flower. So the monkey flower is laying down and getting coated in the minerals, and then the plants perish, leaving behind what is effectively petrified plant remains right there. So these stems have just laid down, and already some of them are turning into stone right here.
But the real miracle of volcanic hot springs is the amazing life that emerges from them. Is it possible for primitive life forms released from receding glaciers to survive in these volcanic hot springs? To answer this question, water temperature of individual hot springs was taken, and algae samples were collected for analysis.
I'm an aquatic ecologist, and I study fresh water. And my PhD thesis in university was on a thermal spring, and I learned a lot about thermal tolerance of small living algae. And it's amazing the variety of algae, but also their tolerance. Each algae species has a specific range of temperature tolerance. If you take them and you put them in cold water, they probably would not survive. They are specifically thermophilic, which means they've grown over centuries, millennia, millions of years in a thermal environment and are adapted to that. The algae that have been identified from there, when I looked at them, the list, they were algae not from lakes, but they were algae from generally a very warm climate and a very high thermal tolerance. The question of how do algae get to where they can live, and what if they land in a hostile environment and don't survive? Algae have many means of transportation. They are mobile. That's important. How did they get to these hot springs? Well, they had to have come probably by air, aerial invasion. It seems to me that we have algae that can survive being frozen in glaciers. We have algae that can survive nearly 50 to 60 degrees Celsius in hot springs. Why shouldn't they be able to survive in the jet stream? We have found them under ice in the Antarctic, in the Arctic. It was the early divers that risked the cold to go and look up at the ice layer from below that were amazed at the beautiful green glow of the ice and the algae growing there. I cite this as an example of just how extremely variable algae are in all types of environment, whether it be seawater, fresh lakes, hot springs, air. They have a unique ability to survive. So it's not surprising to me in Mount Edziza that to see living algae at hot springs that you recorded a temperature of 50 degrees Celsius. It's not surprising at all, because they are extremely resistant to both cold, to burial without oxygen, and of course to high temperature. It's entirely possible that the algae were brought to the mountain during glacial recession, and I see absolutely no reason that you should then have a viable population of photosynthetic algae in these springs. As I was looking over the list of the species that occur in all of the samples from your hot springs, I'm not surprised. The most dominant and abundant are the most primitive. I was a little surprised by the diversity of diatoms, the uniqueness of this environment, and what is seemingly such a hostile environment. With the diversity I see here is very surprising indeed.
Among the diversity of algae discovered in the volcanic hot springs was one rare species from the far Himalaya and another species from Southern California. While the interaction of fire and ice resulted in an abundance of algae species flourishing, the consequences of this unlikely union produced the volcanic glass obsidian that would permanently change the hunting habits of early man.
My English name is Oscar James Dennis. That's what I'm registered as in Canada. And we're sitting on Edziza. It's referred to by most as Mount Edziza. I have a difficult time calling it Mount Edziza. It's Edziza, and Edziza refers to some of the areas where you have the cones and you have the hollowness underneath from the lava flows, and the surface solidified. And then you have the hollowness with the rocks, the burnt out rocks. And when you walk on the rocks, it makes a sound in combination with the hollowness of the mountain. And that's what this Edziza refers to. It refers to the crunch and the hollow combined. The thing that amazes me about this all the outcrops and wherever you see this obsidian scattered all over the ground is, the thing that amazes me is that you tend to think that it's all over, like this place is just like this, but it's not. There's only the only place you find these is near the pipes, and there's one right over here. And that's what fascinates me about this area. And you look around. One of the things that one of my grandmothers told me when I was a young man, she told me that in order for anyone to come onto this mountain, they would have to go through 8 months of ritual, celibacy, 8 months of celibacy within the ritual. And it involved sleeping on one side for 4 months, sleeping on the other side for the other 4 months. And every morning you would cleanse and you would bathe, and in preparation for your trek onto this mountain. And then she also said when you came onto the mountain, it was believed that the mountain was alive. So therefore, whenever you were coming to a pipe, like one of these pipes, you would have to approach it from downwind, like an animal. You couldn't approach it from upwind. And once you get to the obsidian, there was you would harvest it, but you notice there's flakes, that there's worked flakes wherever you look. And the reason why there's all these worked flakes is because they had to carry it down by dog pack or by they had to carry themselves. So to carry a huge piece like this wouldn't be very strategic, because you could only carry so many pieces like this. So what they would do is they would work the pieces down to not to finished products, or maybe in some cases they did, but a lot of the times they would just work it down to manageable pieces, and then they would take it down. The way this is worked is they use antler, and there's 3 stages. I don't have the second tool. The third tool is when you get it down to a blade, then you have to switch from using these antlers. This is taken from a moose horn. So when you're using this tool, you don't hold it like tightly like this and bang the glass. You don't do that. You allow this to drop. It's sort of like you're allowing it to free fall, but you could also put pressure and also velocity to it. So I would leave it on my lap in my hand, and then I would let it drop. So that's why this is bigger. Then when it gets to a certain point, like when I break it down to a certain point, I would switch weights. So this is a lighter piece. So then I would switch to this weight, and then I would keep striking it and control the brake. So that's how it works. This is a biface. It's an artifact that was made by my grandfather. It was found by my uncle. He passed away last year. He was in his, I think, 85, almost 90, and he gave this to me. when he found that I was interested in doing this. So this has been worked, and you see how that center line is down the center? Well, I got this piece on this side almost centered. Once I have it centered like this, then I just need to remove axis. So I almost have this, and this is a blank. So this is a biface, this is a blank, and this is a core. See that? Look at this. So that's how you carve it down. The thing that really, the thing that just dawned on me doing this up here, I'm adding these flakes that I've worked is going to be left up here for the next 10,000 years. I'll always know that. I have a piece of rock in my bag, but it doesn't really matter. This creates a surface for you to hit when you do that. And you see how there's this indentation here, and it makes the line go this way. It's real nice when that happens because here's a lump here that needs to come off. And then you take it off, and you just take it off like that, and that lump's gone, you see. Here's this huge hump here, but I have to take this off before I could get at this. Then you switch it around. You take that off like that. That was beautiful. You know, if you hold those blades up to the sunlight, it would show this real nice green hue, and that was the way that they used to identify this obsidian. This dot, it's delta N. So there it is.
It's amazing to be here on the flank of Edziza, which was really the mother lode for obsidian, volcanic glass that traded all over the country. The thought that, you know, pieces of glass worked on this very flat here would have been traded as far as Haida Gwaii, east across the Rockies, certainly south into middle British Columbia, possibly as far as California. And it's kind of magical to sort of be here and know that obsidian has been worked on this mountain not for 1,000 years, but for 8,500 years. Now this particular place would have been covered by ice at that time, but there would have been great boulders of obsidian spat out by the mountain in a sense, and the original peoples must have walked up these valleys, found those great treasures, because you have to think, these were Paleolithic hunters and gatherers. They depended on the hunt. They needed a tool that could pierce hide, the hide of a caribou, the hide of a sheep, the hide of even a grizzly bear. And when you could take something like a piece of obsidian glass, which we know is the sharpest known substance on Earth, this would have represented a treasury of wealth beyond any other element in the Paleolithic toolkit. And so who controlled the source would have been amongst the most powerful and richest people of their era, whether that era was 4,000 years ago, 2,000 years ago, or 1,000 years ago. And so they would have come up here and they would have found these great cores of obsidian. Now this is a tiny one. Some of these things can be as broad as your arms can reach. And they would have slowly worked this until they had a kind of a piece that they could, a blank as it's called, that you could carry down off the mountain with you. Or you could continue to work it until you had a perfect biface here on the mountain. But a core of obsidian would have been like a lump of gold today, carried along the trade routes throughout the country. And one of the things, when you walk across Edziza, you can sometimes walk for kilometers at a time where it seems like 25% of the ground cover is shards of obsidian. And your first thought is, that can't be all of human creation, but it is. And having just watched Oscar take a core of obsidian and turn it into this sort of blank, this is the very piece he chipped, and all around him remain the elements of what had been the core. And so if you multiply that by thousands of people over thousands of years, working this mother lode, it becomes a sort of carpet of the human imagination and technology spread across the mountain that is sacred to the Tahltan.
The second question about the intersection of ice and fire that the team of scientists focused upon was the distribution of obsidian by native cultures. To determine just how far Edziza obsidian was traded, Dr. Rudy Reimer brought an advanced detection device called X-ray fluorescence to the mountain to capture Edziza obsidian's unique fingerprint.
We're here at Mount Edziza looking and hunting for obsidian. And this place, Mount Edziza, is an incredible, large, and very culturally important source of this volcanic glass. What makes Mount Edziza obsidian so unique is that there are multiple flows all throughout the volcanic complex that we can analyze with our portable X-ray fluorescence instrument here. And this allows us to do this analysis in the field and apply it elsewhere in our research to understand the broader scale in which this material was distributed. So the work that we do here, close to the source, to characterize and obtain elemental fingerprints of this material, is of the utmost importance, not only for archaeologists, but for First Nations people who've been utilizing this place for up to 10,000 years. So one of the advantages of newer technology, such as this portable XRF handheld unit, is that we can bring the instrument into the field. And this is opposed to 20, 30 years ago, where we had to come out on long expeditions, collect a large number of samples, pack them out, and bring them back to our labs. And many of those analyses took a long time. The computing power wasn't as good as it is nowadays. And in other techniques, it would destroy the artifact. The benefits we have now is that it's portable, quick, and non-destructive. So we can do mass analysis either in the lab or here in the field. So now we're going to do a test on this large boulder of obsidian to be able to compare its chemical signature to other samples throughout the volcanic complex. And so here we're at the headwaters of this creek, which would have provided a nice travel corridor up to Goat Mountain there, that is known as one of the main quarry sites throughout the complex. We're here at an archaeological site just above the creek where we were earlier doing some tests. Most of the material down there were raw nodules, probably eroded down by the glaciers in the creek from higher up where the source outcrops are in and around Goat Mountain. But this is much different. What we're looking at here is the result of human activity. And we as archaeologists can recognize the breakage patterns of obsidian and the way people worked this incredible material thousands of years ago. And it's the patterning of the breakage in flakes and debris such as we see here that distinguishes it from natural breakage. And so when we find concentrations of flakes and tools and cores, such as this lithic scatter, we can be very confident that this is the result of human activity.
Hi, my name is Jordan Hanley, and I'm an undergraduate student here at Simon Fraser University. I'm currently working with Dr. Rudy Reimer, establishing the obsidian trade trails from Mount Edziza and throughout BC and Alberta.
So now we're ready for analysis of some obsidian that we're not sure where it's from, but we can obtain elemental spectra and match it to a known source and compare it to other sources that we have in our reference library. Now that we've run a sample, we can examine the spectra of elements that appear within that sample. Most notable are these two large peaks here, which are iron, and this other very large peak here, which is zirconium. And these two peaks are very distinctive to the Mount Edziza source. It allows us to compare this spectra to other spectra of obsidians that occur across Western North America. So for example, I can move Mount Edziza
it to the background, which is now outlined in blue, and compare it to another obsidian source in southern Oregon known as John Day Reservoir. And instantly you can see the same elements all have different concentrations. And we can compare these spectral peaks to one another to distinguish geological samples and archaeological sites.
Once the fingerprint of Edziza obsidian had been collected in the field and verified in the laboratory, artifacts from archaeological collections across the continental Northwest were sampled, and an early pattern of native trade routes began to emerge.
Past geochemical studies have established that the obsidian is in northern Alberta, all the way up to Yukon and Alaska, throughout interior and central BC, and all the way down the coast. So we hope to expand those understandings of that distribution.
The story of Mount Edziza is the story of flow. Water flows just as glaciers flow. Rocks turn to fluid lava rivers. Superheated steam flows out of the volcanic vents. But most of all, time flows. And over a period of 8 million years, it created today's Mount Edziza complex. To enter the heart of the caldera, to take its pulse, understand its soul, one soon realizes that they are the solitary soul. The sole speck of life in an ancient cathedral. Not the call of a bird, the hum of an insect, not even the track of an animal marks the moving moraine. And yet here, in the heart of the Mountain King, surrounded by towering walls of breathless beauty, where shrouds of mist spike with the smell of fresh sulfur, and vast, yawning crevasse caverns inhale the thunder of water cascading from the rim rock, one realizes that the mountain itself is alive, and has been long before the coming of man. But what is the mountain's future? Presently, it is semi-dormant, but it is certainly not dead. It is likely that Mount Edziza will continue to erupt, but when is not certain.
Mount Edziza is still active, and there's a good chance at some point in the future, maybe in 10 years, maybe in 100 years, maybe in 1,000 years, that Mount Edziza is going to produce more eruptions.
What is certain is that vulcanization is one of the few primary forces in nature that is not controlled or even influenced by humans. And whatever the future of the mountain, it will continue on its charted course, oblivious to human endeavor.